Hello, as you know, in the last videos, we've covered the last little bit of chapter 6. So in today's video, we're going to start with chapter 7, which is moving in a totally different direction than either the gas laws or thermochemistry. So now we're moving into the wave-particle duality of nature of light. So most of you have heard at some point in your life or another that light, the visible light, travels as a wave and a particle. So today we're going to discuss those two different aspects. We're going to discuss the wave nature first in this video, and then in the second video we're going to be discussing the particle nature and how we can do some calculations using those two different theories or two different ways of understanding how light actually works. So in order for us to talk about the wave nature of light, we have to understand what a wave is. I'm going to draw a simple structure. So this is the 0 point. A wave will look something like this. It travels in a sinusoidal pattern, and it has certain aspects of this wave we're going to be dealing with. First off, let's label some of the points on this wave. The top part, the peaks of the wave are called the crest. The bottom parts, or the wells of the wave, are called the trough. So we have a crest and a trough. Now, every wave has a certain wavelength associated with it. So that is the distance between the two different crests. So this is called wavelength, and it's given the Greek letter lambda. So that's, for those of you in the Greek system, you know that this is lambda. So lambda is equal to wavelength. Wavelength. Okay, that is the distance between the crests. Another thing that we can see or that we can calculate for waves is the frequency of the wave. So in this, we have a given oscillation, a time that it takes this wave to oscillate. Now, what we can do is certain waves will have a shorter or a longer frequency. What that means, I don't want to draw it on the same plot because I will get messed up that way. If we have the same height and trough size, but we increase the frequency. So now in the same distance, let's say this is our distance, we have the same, roughly the same distance, we have a lot more crests going on here. This is called the frequency. So our frequency has now increased. We have a greater frequency here because there are more crests for a given time frame. So that is given nu. That's a script V, and that is called the frequency. Frequency. Wavelengths are generally given in nanometers for visible light. Frequencies are given in inverse seconds, which for those of you who are physicists know that an inverse second is a hertz. So wavelengths are in lengths, regular normal lengths, nanometers. Frequencies are in this inverse seconds, and we call them hertz. So we have these two different topics that we can talk about, the wavelength and the frequency of a given wave. Now, these two are related to each other. As the frequency goes up, the wavelength has to go down. We can see that here. The distance between the crest of these two the distance between these two crests is a lot longer than the distance between these two crests. And we know that this has greater frequency, so the frequency went up on the second graph, which means the wavelength had to have gone down. So as frequency increases, wavelength decreases. And of course, the vice versa. As frequency decreases, wavelength increases. Okay. How do we actually identify this? There's this inverse proportionality between these two. One goes up, one goes down. They are both related to the speed of light. That is the fastest thing that is in our known universe. So the speed of light is going to be represented by the letter c, lowercase c. This is going to be the speed of light. And since it is a speed, a velocity, we need to know, we have units of meters per second here. So If we were to simply multiply the wavelength, which is in nanometers, change the nanometers to meters, and then multiply that by the frequency, we would end up getting the correct units. So our equation is the speed of light, which we actually know the speed of light is going to be, for this class, 3.00 times 10 to the 8th meters per second. To go back to what I was saying, if we multiply these two variables together, we can actually see that they're related to the speed of light. Speed of light is equal to nu, which is the frequency, times lambda, which is the wavelength. The wavelength should be in meters. The frequency should be in inverse seconds. So this is going to be one of our key equations that we're going to use in order to solve certain problems. If you're given a wavelength, you can tell me what frequency of light it is. If you're given a frequency, you can tell me what wavelength of light it is. Now, for the human eye, we can only see a certain range, the visible spectrum of light. That range is the visible spectrum. Visible is going to range from 400 to approximately 750 nanometers. So from this, you should be able to identify what the frequency is by using our letter C. Now there is one more aspect of a wave that I would like to talk about in this video. So we have wavelength. This is between the crests. We have frequencies. This is the amount of oscillations per given time. And then our last one that I want to talk about is the amplitude. Now we're not going to really deal a whole lot with amplitude in this class. However, I still want you to be aware of it. So if we have a line here, and we have our wave, our normal wave, let's say that this is pretty vibrant. Let's say we're in a red light, and this is a very bright red light. Now, the amplitude is actually the distance from this 0 point to the height of that peak, of that crest. Now, what we can do is we can actually reduce that amplitude so we get the same oscillations with a lower drawing these is not as easy as it looks. So with a lower peak height. This is how we determine amplitude. Amplitude. So this bottom one, the smaller one, that's not quite as tall, will actually look dimmer to your eye. So the higher the amplitude, the more vibrant the color is, the brighter the light is. The less the amplitude, the dimmer the light is. And that is all I want to talk about the wave nature of light. So we have this nice equation, speed of light is equal to nu lambda. And with that, I will see you all in class tomorrow.